From the picture here, you can see the instruction set of cortex M3, M0. The first one is logical shift left. The format of this instruction is 5 constant of OV code and 5 bit of number and 3 bit RM and 3 bit RD. So we can say this instruction set is 5C, 5 number, 3M, 3D. Okay, the first 3 are all the same format. The second one, you can say it is 7C, 3RM, 3RN, 3RD. Okay. If you manually coded it, you can just enter the number to the corresponding bit region. That's quite easy. The same for our program. From here, you can see this is the defining word. It is used to define the assembler, like this one, or this one, and the others. From here, you don't have to really understand what the scheme of this program, but you have to know how to fill the corresponding bits region with the corresponding register and the number. So just fill RD to bit 0 and 2, and RM to bit 3 and to 5. The same number from 6 to 8 in hexadecimal. So once you fill these regions with the corresponding numbers, then you can use this to define a new instruction, new assembler of an instruction. So let's load this program first. Okay, once we load it, we can execute it. This one, we can use this. Okay, we can add the number for the instruction. It has R1 here, and this is R is 2, R2, and number is 3. So when you execute it, and you can see where you are. See? Now, if we use the same instruction again, then you'll find that the address is advanced by 2 or 4, 6 to 8. So in this area, the compiled code or assembler code is 00D1. Also, we can use the same instruction like this. This is the algebraic assembler. So when we dump it like it was, you find D1, D1, D1. So it means that the instruction format or no, the instruction like this and this are the same. But I personally prefer to use the algebraic assembler because it can be used in all the MCU. Now, let's switch to X5, C5. We start from the beginning. I load it. Oh, yes, first we have to know what is the defining word here. In the previous one, we have no these two lines of program. These two lines are used to generate disassembler when the defining word is defined. Oh no, the disassembler is executed, the assembler is executed, then the disassembler is generated. It's generated like this. When you execute the assembler of this one, it will generate this disassembler. So when you execute it, something like this, you can disassemble it to see the instruction like this, the disassemble list. Okay, now we can load the program first. Here. Oh, sorry. Okay, first we have load this program first. If we want to generate the disassembler. So we load it with xe1.f. Now we will again load this one. Okay, the defining word has been loaded. Then we can use this defining word to define a new instruction, like this one. Okay, like this one. And now we can copy it and paste it. See, this is the generated disassembler of the instruction, of this kind of instruction. The same, we can use this one. Here. See, the generated disassembler of the instruction. And you'll see it has original mnemonic here because we turn it on, original mnemonic on. we now have to load it. Then we can execute it. So this is the first one and the second one. Okay, we've loaded two disassembler, this one and this one. Now we want to execute an instruction like this one. The assembly language, we can say this is assembly language. We can use it. Okay. Here. We prime means the target image. So we are now in target area address 2. And then we can see what happens in this area. Oh. Zero is okay. 0 is the 1. The same we can use the original mnemonic like this one. So okay. Now this is in address 2. So we can say it same. From 2, we can sum it to C. No sum, no such instruction here. No. Anyway, we have 2 instructions of assembler, and the generated disassembler. So if we have more like this, then it will generate more assembler, more disassembler. Each one generate the assembler of this one, and the second this one, but it also generate its own disassembler. Okay. Or if you want to use the file to load the whole program, then we can do it like this. Okay, we can start from the new one. Okay. Oh, I see. Upload the first. Upload the XC1 first. XC1 is the basic disassembler, the ready program. So we have loaded first. Now we then load the second one. See? So the newer instruction has been, this assembler has been loaded and this assembly is generated at the same time. Okay. Now, we even can include the assembler of these two instructions from RISC-V by say, oh, that's a lot. Okay. This is the generated disassembler of RISC-V MCU. Then we have the disassembler here. This is a disassembler. So we can also load it. Okay. So we can now use the 4 instruction set of RISC-V, including 16-bit and 32-bit before instruction were made. Now, let's say where we are now. From 0, we say R1 equal R2, left shift 3. Okay. Okay. So we can say 0 from 0, we can disassemble it. See, 1, 2, 3, R equal to R, left shift. So you can use the algebraic assembler like this, or if you prefer the POSIX notation, or this. Now we can say it is now in 2 and disassemble it. See? Oh. What? Okay, why? Oh, it is 4, now 2. See, so we say, well, we are now. We are 8, when S is 8. Oh, S. Oh, it's 4 bytes. So our next address should be 4. Here, it's 4. Oh, it's, see, it's the same like this. This is 4 bytes. Because of it is assembled to 32-bit or 4 bytes of instruction. So that's why the address is 11 by 4 instead of 2. Okay. We can use the original mnemonic like this. You say OM, original mnemonic. It's a toggle switch. So we say 0 DS. shift left, immediate. This is shift left, immediate. Oh, yes, it's different than different name of than that of the instruction of Cortex M0. It's completely different microprocessor. So that's why you use different name. This is the big difference that if you use the same the algebra assembler like this, we use the same mnemonic in Cortex M0, but in Cortex in RISC-V, we still use the same name or same mnemonic, but it's different in traditional mnemonic. So once you learn the algebra assembly, you don't have to learn the other mnemonic of different microprocessor, different MCU. So it's good to use algebra assembler for all kinds of MCU. Okay, that's it. Thank you.